You know, when you think about quantum mechanics, you probably picture stuff that's way too small for us to ever see, right? Hidden away in the world of atoms. But what if I told you that sometimes the quantum world gets big? So big that its bizarre rules spill out into our world, creating effects that look, for all intents and purposes, like pure magic.
I mean, just look at this. It's a magnet, just hanging there, floating over this little black puck. There are no strings, no hidden fans, nothing. It's completely defying gravity. So what in the world is going on? What kind of force can do this so perfectly? Well, the answer is found at temperatures colder than anything you can imagine.
What you're seeing is one of the most incredible phenomena in all of physics, superconductivity. This is where a material enters a collective quantum state, and electricity can flow through it with absolutely zero friction, no resistance at all. It's a behavior that's totally impossible in our day-to-day lives.
So, to really understand how that magnet is just floating there, we first need to get a handle on the magic of what makes a superconductor, well, super.
Okay, the difference a few degrees of temperature can make is just mind-blowing. In any normal metal, like a copper wire, electrons are constantly bumping into atoms. That's resistance. It creates friction and you lose energy as heat. And a magnetic field? It passes right through, no problem. But if you cool that same material below a special critical temperature, everything changes. It becomes a superconductor. Resistance vanishes. Poof, gone. But something even weirder happens. It starts to actively and aggressively push any magnetic field out from inside itself.
This amazing trick is called the Meissner Effect, and it is the secret sauce behind our floating magnet. Now, this is way more than just simple repulsion, like trying to push two north poles of a magnet together. The superconductor creates these perfect little currents on its surface that generate an opposing magnetic field. It perfectly cancels out the field from the magnet above it, creating this incredibly stable cushion of force that lets the magnet just levitate.
But here's the crazy part. When this was first discovered, scientists had no idea why it was happening. It wasn't an answer to anything. It was the beginning of a huge mystery that would stump the smartest people on the planet for half a century.
This timeline really tells the story. Back in 1911, zero resistance was seen in mercury. This completely shattered what physicists thought would happen. They figured electrons would just sort of freeze in place at absolute zero. Then in 1933, the Meissner Effect is discovered, making the whole thing even stranger. But look at that gap. It took until 1957 for a working theory to explain how any of this was possible. For 46 years, this was one of the biggest unsolved problems in physics.
And this quote shows you just how tough the problem was. This is Albert Einstein writing way back in 1922, basically admitting that the quantum mechanics of the day wasn't even close to being able to figure this out. The greatest minds on Earth were baffled. How could electrons, which all have a negative charge and should repel each other, suddenly start working together to flow perfectly?
The solution, when it finally came, was just so elegant and completely unexpected. It was like someone finally figured out the choreography to a secret dance that had been happening inside the metal all along.
The big breakthrough came from three physicists, John Bardeen, Leon Cooper, and Robert Schrieffer. Their idea, now famously known as BCS theory, was built on a concept that sounded completely nuts. They proposed that inside a superconductor, electrons pair up. Two particles that should hate each other suddenly become partners.
So, how on earth do two electrons pair up? Well, they get a little help from the material itself. Picture this. The first electron zips through the metal's crystal lattice. As it goes, its negative charge pulls on the positive atoms in the lattice, kind of creating a tiny ripple, or a dent. That's a phonon. For just a split second, that ripple creates a little pocket of positive charge. And then a second electron floating by is drawn into that positive zone, indirectly linking it to the first electron. The lattice itself plays matchmaker.
And this pairing changes everything. These Cooper pairs start acting like a totally new particle, called a boson. Now, unlike individual electrons, which have to stay in their own lanes, bosons are social. They can all pile into the very same low-energy quantum state. They effectively merge into one giant collective wave, all flowing together in perfect unison. To knock just one pair off course, you'd have to disrupt the entire system. And the tiny vibrations from the atoms just aren't strong enough to do it. The flow is perfect, resistance is gone.
But this quantum magic is an incredibly delicate state of being. It only works if you follow a very strict set of rules. If you push it too hard, the whole thing vanishes in an instant.
So, every superconductor has three limits that are all tied together. There's the critical temperature. Get too warm and those Cooper pairs break apart. There's a critical current. If you try to pump too much electricity through it, it snaps back to being a normal metal. And finally, there's a critical magnetic field. If the field outside is too strong, it just overpowers the Meissner effect and the superconducting state collapses. This is the operating window you have to stay inside for any of this to work.
It also turns out that superconductors come in two main flavors. Type 1 are usually pure elements, like the mercury they first studied. They have that perfect Meissner effect, but their critical magnetic fields are really low, so they aren't very useful. But type 2, now these are the technological workhorses. They're alloys and ceramics that have a clever trick. They let the magnetic field punch through in tiny contained tubes, called vortices, while the rest of the material stays perfectly superconducting. This allows them to handle way stronger magnetic fields, which is why they're essential for things like MRI machines and particle accelerators.
But the story doesn't end there. Not even close. The original puzzle might have been solved in '57, but a totally new one popped up that is pushing physicists to their absolute limits today.
For decades, the Holy Grail has been finding materials that can do this magic at higher and higher temperatures. The early ones needed super expensive liquid helium to get down near absolute zero. But the massive game changer came in 1986 with materials like this one, YbCO. The key thing here? It works at 93 Kelvin. That is just above the boiling point of liquid nitrogen, which is incredibly cheap and easy to work with compared to helium. This blew the doors wide open for real-world applications and really fueled the dream of finding a room-temperature superconductor.
But there's a catch. That beautiful, elegant BCS theory, the electron dance with the lattice acting as matchmaker, it doesn't seem to fully explain how these new high-temperature materials work. Something else, something more complex seems to be going on. So just as one 50-year-long mystery was solved, another one began. And figuring this one out is one of the single biggest goals in physics right now.
And that brings us to the big final question. The first quantum revolution gave us the transistor, the laser, basically the entire digital world we live in today. The race is on, right now, to find a material that can do all this at room temperature. And if or when we find it, what does that second quantum revolution look like? Power grids with zero energy loss? Maglev trains that float silently across countries? Unimaginably powerful new computers and medical devices? The possibilities are staggering, and it all comes back to that weird, beautiful quantum dance happening just a few degrees above absolute zero.